These are the examples for Algebra 2A, Credit 3, Lesson 6.4. Lesson 6.4, we're going to be doing several different types of factoring. Let's take a look at an example for number 1. We have x to the third plus 13x squared plus 42x. First thing we check for when factoring is common factors, and notice that each term has an x in it. There's 3 x's here, there's 2 here. We just can tell that from the exponent. There's no exponent here, so we know that that's 1. So the common factor with variables is the lowest, the fewest number of x's. So 3, 2, 1. So x to the first or just x would be a common factor. Another way of thinking of that is there's at least one x in each term. That's why we wouldn't say x squared is a common factor, because while there's at least 2 x's in the first 2 terms, there's not 2 in the third term. So that's why we take the smallest exponent. So we took one x out, so we're going to reduce each of these exponents by 1. So we have x squared, and then x to the first, or just x, and then x to the 0. But if that was 1, that goes to 0. If it's x to the 0, we don't need to write it. So now we have a trinomial, and we can factor that into 2 binomials. And so let's go ahead and see how we do that. So we're looking for 2 numbers that add to the coefficient of the x term. So 2 numbers that add to 13 and multiply to positive 42. Now, in the page, on the page that's immediately before this lesson, there is a chart that says factors 1 to 100. And they're actually, what that is not just factors, but they're listed in pairs. And so you can use that to help you to do these problems. So in this case, we're multiplying to 42, so we want factors of 42. So looking on that page, you would see next to 42, you would see 1 and 42, 2 and 21, 3 and 14, and 6 and 7. Now we have to determine which of these pairs that all 4 of them add to 40 or multiply to 42, which of those pairs adds to 13? Well, 1 plus 42 is 43, 2 plus 21 is 23, 3 plus 14 is 17. So none of those work, but 6 plus 7, fortunately, is 13. And so our factors that we're looking for here are 6 and 7. Again, why does that work? Because 6 times 7 is 42, 6 plus 7 is 13. So the way we write that is with the x, so x plus 6, and then x plus 7. And that would be our answer to number 1. X times x plus 6 times x plus 7. A similar situation going on with problem number 2. Let's just move that over. I don't know if we were able to see that. Just if you need to see that there, or so you can see that there, you can see all the factoring work that we did. All right. So if you need to pause that, we'll just give you a second to do that if you wanted to see those factors. All right. Now moving on to our example for number 2. Once again, we have x's in each term. 3 of them here, 2 here, 1 here. So the smallest 3, 2, 1 would be 1. So we're going to factor out 1x. And since an x was taken out of each term, we reduce each of these exponents by 1. So we have x to the second plus 4x to the first, or just 4x. And then minus 45x to the 0. But again, if it's x to the 0, we don't need to write it. All right, so now let's see if we can factor this into a pair of binomials. This time we're looking for 2 numbers that add to 4 and multiply, to negative 45. All right, so let's take a look at our factors. We start with the multiplication. So again, we could look on our factors 1 to 100 sheet, and we would see that factors of 45 are 1 and 45, 3 and 15, and then 5 and 9. And I believe that is all of them. Now, if we're multiplying to a negative number, in each pair, one of the numbers, and only one, has to be negative. Well, which one is it? Since we're adding to a positive number, we need more positives than negatives. So the larger number will be the positive, which means the smaller number will be our negative. And now we're going to add these up to see which of these pairs adds to positive 4. Negative 1 plus 45 is 44. Negative 3 plus 15 is 12. And negative 5 plus 9, positive 4. So our factors are negative 5 and positive 9. And so writing those out as binomials, with the x's, we have x minus 5. Careful, make sure we make that minus. And then x plus 9. And so that is our answer to number 2. Our example for number 2, I should say. All right, so now let's go ahead and take a look at an example for problems 3 and 4. Get all of this erased here. So on problems 3 and 4, we're going to be looking at a factoring pattern called the difference of two perfect squares. So our example for number 3 is 7x to the third minus 448x. All right, so now, once again, we're going to check for common factors. There's 3 x's here, just 1 here, so the fewest is 1, so we're going to factor out 1x. Also, now this didn't come up, we didn't talk about it in the examples for problems 1 and 2, but we also want to check to see if there's a common factor between 7 and 448. Now, fortunately, the only factors of 7 are 1 and 7, and we don't care about testing 1 because factoring out a 1 doesn't change anything. So let's see if 7 goes into 448. And so we take 448, we divide that by 7, and we find that, in fact, that it's 64. So 7 is a common factor, so we're also going to factor out the 7. So in this first term, the 7 has been factored out along with one of the x's, so we just have x squared. Remember, if we factor out a 1x, we reduce that exponent by 1. And we just said that 448 divided by 7 is 64, but remember that's a negative divided by a positive, so that's a negative. And the only x here was factored out, so this is what remains inside. Now, notice here we have subtraction, or what we call the difference, of two perfect squares. How do we know that x squared is a perfect square? Well, it turns out that any variable with an even number for an exponent, like 2, 4, 6, 8, is a perfect square. And 64 is also a perfect square. In fact, before we go on, let's list out our perfect squares from 1 to 100, which you could would definitely help you out on problems 3 and 4. So how do we find the perfect squares? Well, we can just multiply numbers starting with 1 by themselves. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10 is 100. Of course, that keeps going, but that's all we're going to need for the examples and that you'll need for your work. All right, so now we notice that 64 is a perfect square. Now, we're not going to use 64, but we want the square root of 64, which is 8. And so the way we write this is x plus 8 and x minus 8. Notice that this does work out even using the rules that we did for factoring on problems 1 and 2. In this case, and again, we're done with number 3, but just to show you how this works, there is no x term here. There's an x squared, but no x term in the parentheses. So that means the coefficient is 0, so we would need two numbers that add to 0 and multiply to that constant term of negative 64. And notice 8 and negative 8 do meet that condition. 8 times negative 8 is negative 64. And if we add 8 and negative 8, we do get 0. The pattern for a difference of two squares just gives us a quicker way of doing that. All right, let's just box our perfect squares here. So we have that. And now let's take a look at an example for problem number 4. For number 4, it's going to be very similar to what we just did. We have 4x to the third minus 324x. So there's 3 x's in the first term, 1 in the second. So there's at least 1 x in each term. So we'll factor out the x. Now, let's see if 4 goes into 324. We'll start with 4. Now, 4 has other factors besides 1. We have 1 times 4, 2 times 2. But let's start with 4 to see if that will go into 324. And sure enough, it does. 324 divided by 4 is 81. So we'll keep that in mind. We'll factor out the 4. And so the 4 has been factored out of this first term. One of the x's, so we reduce our exponent by 1. Again, we just said 324 divided by 4 is 81, and that's a negative divided by a positive, so that's a negative. And our only x was factored out. Now we're going to use our difference of two squares pattern to finish this one up. So again, it's always x plus and x minus. 81, what's the square root of 81? The square root of 81 is 9. So that would be x plus 9 and x minus 9. All right, so that is our examples for problems 3 and 4. Some of these other square roots, we'll just fill those in for you. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, and then we've got 4, 5, 6, 7. These are done, and then 10. So that should help you out when you do problems 3 and 4. All right, going over to the next page, problems 5 and 6. So we just talked about a pattern called the difference of two perfect squares. Next example, we're going to be looking at a pattern called the sum of two cubes. And so that's there in your packet, the pattern. Let's take a look at our example here. We have 343 x to the third minus 512. All right, so that's going to be our example for problem number 5. So now we look at that, we find that there are no common factors. You could probably even Google that, is, what are the common factors of 343 and 512? There are none. But what we want here is, so we did perfect squares in the last one. So what we're going to do now is look at perfect cubes. So perfect cubes, 1 times 1 times 1 is 1. So we're multiplying not just by itself, but 3 of them. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. Interesting, 64 is both a perfect square and a perfect cube. This is 5 times 5 times 5, 6 times 6 times 6, 7 times 7 times 7, which is 343. Is that, I'm sorry, let's see, 5 times, yeah, that's right. And then 7 times 7 times 7 is 343. 8 times 8 times 8, there we go, is 512. 9 times 9 times 9 is 729. 10 times 10 times 10 is 1,000. All right, so now what we're going to do here is rewrite these as the difference of two perfect cubes. And so the cube root of 343 is 7. So we have 7x raised to the third power. The cube root of 512 is 8. And so we have 8 raised to the third power. And so our pattern, let's go ahead and write it up here. So we have a plus b, excuse me, a, is that right? Yes, a minus b. So let's go ahead and put the whole pattern up here, actually. So we have a cubed minus b cubed. The pattern is a minus b, and then a squared plus ab plus b squared. Now, what are a and b? So a is the first term, that's the 7x. B is the second term, the 8. And again, just the 8, not 8 to the third, or just the 7x, not 7x to the third. So we have a minus b, so 7x minus 8, and then a squared, so 7x squared, plus a times b, 7x times 8, and then plus b squared, 8 squared, to finish it up. And that's our answer. We just need to simplify that. And so let's go ahead and do that. Now the 7x minus 8 in the binomial, nothing to do there. But 7x squared, 7 times 7 is 49, so 49x squared. 7 times 8 is 56, so 56x. And 8 squared, 8 times 8 is 64. So our answer here, our factors would be 7x minus 8 times 49x squared plus 56x plus 64. All right, so now our example for number 6, and we'll just do that over here, is, so we had difference of two perfect cubes. Now we're going to do, it turns out there's also a pattern for the sum of two perfect cubes. So we have 729x cubed plus 1,000. So looking at our list of perfect cubes here, and we'll kind of try and box this in a little bit to see that better. So the cube root of 729, we put the little 3 there to indicate cube root, indicate cube root, there we go. And then the cube root of 1,000 is 10, because 10 times 10 times 10 is 1,000. So we're going to rewrite this as 9x cubed plus 10 cubed. And we'll put our pattern up here for sum of two cubes. Now it's going to be very similar to our pattern for difference of two cubes, but we're going to see some differences with the plus and minus signs. So we have a plus b, and then times a squared minus a times b plus b squared. So in essence, these signs switched, whereas with the difference, this was minus and this one was plus. All right, so let's go ahead. Remember, this is our a and this is our b. So we have 9x plus 10. Make sure we can see that okay. And then a squared, so a is 9x squared minus a times b, so 9x times 10, and then plus b squared, so 10 squared. So simplifying, nothing to simplify in the binomials. We just bring down 9x plus 10. Here, 9 squared, which means 9 times 9 is 81, so 81x squared. Negative 9 times 10 is negative 90. Don't forget the x. And 10 squared, which means 10 times 10 is 100. So our answer, 9x plus 10 times 81x squared minus 90x plus 100. And so that's an example for the sum of two cubes, what you're doing on number 6. Some of these other cube roots here, let's fill those in for you. The cube root of 1 is 1. Cube root of 8, as we already saw, is 2. Cube root of 27 is 3, because 3 times 3 times 3 is 27. Cube root of 64 is 4. Cube root of 125 is 5. And the cube root of 216, whoops, this should be cube roots there, is 6. All right, so that is it for problems 5 and 6. And now let's take a look at our last type of factoring on problem 7 and problems 8. All right, so our example for problem 7, we have 3x to the 5th minus 6x to the 4th minus x plus 2. So on this one, whenever we have 4 terms, we're going to assume right now that we're going to be doing factoring by grouping. And what we mean by that, we're going to factor out common factors from only the first 2 terms and then from the second 2 terms. And you might even look at the second 2 terms and say, what common factor is that? But we'll definitely show you what that is. And so let's go ahead and take a look. The first 2 terms, there's 5 x's here, 4 here. So the fewest is 4. So x to the 4th is factored out. The largest factor of 3 and 6, the largest number that we can divide 3 and 6 by is 3. So let's see what remains inside the parentheses for the first 2 terms. The 3 was factored out. Of these 5 x's, 4 were factored out. So there's only 1 left there. 5 minus 4 is 1. Here, negative 6 divided by 3 is negative 2. And all 4 x's were factored out. So this is x to the 0, or just nothing there. Now, what about here? How are we going to factor something out of negative x plus 2? Well, what we want to create actually is the same thing inside the parentheses. And it's very close. The problem is instead of a positive x, this is a negative x. And instead of a negative 2, this is a positive 2. So now we said earlier that we rarely, we didn't say never, factor out a 1. And typically not a 1, but there's a little trick. We can factor out a negative 1. And you might remember that we said earlier, well, factoring out a negative just changes the sign. Well, we didn't say that earlier, but factoring out a 1 doesn't change anything. And factoring out a negative 1 will only change the signs. And so that's actually going to be very nice here. Factoring out a negative makes the x positive and the 2 negative. And now, if we look at this, kind of look at these as 2 separate entities in a way, notice that in each of these there's an x minus 2. That is going to be our common factor. So we factor that out, and then what remains here is just 3x to the 4th, and then here a minus 1, and then that's it. That's all you do. That's factoring by grouping. All right, let's take a look at an example for our last problem, number 8, and that is going to be another factoring by grouping problem. And so let's go ahead and do that. We have, this is our example for number 8. We have 10x to the 3rd minus 5x squared plus 8x minus 4. All right, so once again, factoring by grouping. look at the first two terms. We have 3x's here, 2 here. So the fewest is 2. So we're going to factor out x squared. 5 and 10, the largest number we can divide into 5 and 10 is 5. So now let's see what remains after we factor out a 5x squared. 10 divided by 5 is 2. Of the 3x's, 2 are factored out, so 1 remains. Here, negative 5 divided by 5 is negative 1. There's 2 x's here. They were both factored out, so it's x to the 0, or again, we don't have to write anything. Now over here in our second part here, x is not a common factor, just like we saw in the similar situation in the example for number 7. But 4 is. The largest number that we can factor or divide into 4 and 8 is 4. And so we can factor out just the 4. So 8 divided by 4 is 2. There's an x here. It was not factored out, so it's still in the parentheses. Here, negative 4 divided by 4 is negative 1, and that's it. And notice we got what we hoped for, the same thing inside both parentheses. So 2x minus 1 is our common factor. And then what remains over here is the 5x squared. And then what remains here is the plus 4. So our answer, 2x minus 1 times 5x squared plus 4. All right, that's a lot of factoring. And those are the examples for lesson 6.4. And so again, pause, rewind, rewatch as needed. Study the examples, and you will do great with this work. I'm sure of it. And again, if you have questions, ask. And good luck with the work. And until the next video, take care and God bless.